Thank you so much, Julie, for the introduction, and thanks all the organizers for this very nice idea of putting all these young researchers together. And as she said, I'm going to talk about the emergence of synchronization in a fluid type PDE for coupled oscillators. Of course, I put the words fluid type PDE to catch your attention, because I understand most of you are from fluid type community, but there's some relation, and the equation I will introduce you just in some minutes is a partial differential equation of loss of type, so it's a kinetic equation. It's a sort of continuity equation that enjoys some similarities with the equations in fluid mechanics. So in particular, my talk will handle the following topic. This collective dynamics. So collective dynamics is the emergent phenomena that arise when a large population of individuals interact and self-organize, developing large-scale structures. So just to illustrate this idea, I will show you a couple of examples. So first, the first example is the following one. Let me open it. So you can see I hope you can see. This is a flock of starlings, and as you may have seen before, they self-organize, forming this sort of structures in a sort of fluid flotating in the air. And at the end, they self-organize and they flock. So it means they align all their velocity, forming a coherent group. But the most important example I will talk about in this talk is the second one. So here you can see some neurons. Actually, they are neurons from the brain of a mouse. And as you can see, although neurons are not necessarily adjacent, they can communicate, and they fire in a synchronized way. So the emergent phenomena here is a synchronization phenomena. So here in this talk, I will introduce you into a very specific model for synchronization. It's called the Kuramoto model. And in particular, it was first introduced by Kuramoto to describe synchronization of chemical signals, but later it was generalized to apply to many other situations, like neural synchronization in the example before, or into more ecological applications, like in the shining of fireflies, right? Synchronization of shining. So first, I will talk about the agent-based model. It means a discrete ensemble of agents. And later, I will introduce you into the fluid type PDE, the macroscopic equation that's called Kuramoto-Sakaguchi equation. And finally, I will end introducing some recent results about the emergence of synchronization in this model. So specifically, I will show first emergence of concentration, and later we will use it to show the convergence towards a global equilibrium. So first of all, let me introduce you into the Kuramoto model. We start with the discrete system of N oscillators. So this model is a coupled system for N differential equations, ordinary differential equations, ODEs, for the phase of each of the oscillators. So here you can see the phases that I denote with the variable theta I, one for each oscillator. And on the right-hand side, we find some sign-type forcing term and some new variable omega I that I will call the natural frequencies. So here there is a very important parameter that is called the coupling strength. So in particular, if the coupling strength is 0, all the oscillators, I will call them oscillators, are uncoupled, and they all move at their natural frequency omega I. Otherwise, if K is positive, there will be some coupling between the oscillators, and some emergent phenomena is expected to happen. So since theta I represents the phases, it can be the phase of the electric signal of the neurons in the example I showed before. I will think of phases as periodic variable, and the way to do is obviously just by projecting the phase theta I or theta, into the unit terms. So I identify theta with the complex number e to the power I theta. I'm using complex notation just for simplicity. So here I rely you to understand what's the dynamics in this model. So let me open again. Here I have some video that I got from Wikipedia, and it's a simulation. As you can see, there are several different behavior depending on how large the coupling strength is. So if the coupling strength is not very large, this is the first case, you barely see any emergence of coordinated motion, right? It's very random motion. Actually, all the particles, all the oscillators are moving at their natural frequency to be omega I, no? However, when K gets larger, we can see some aggregation around some points, but still this value of K is not very large, so still there are some oscillators that escape from that arc, right? But as soon as K is larger, we observe that all the oscillators aggregate, they concentrate around some points, and they all rotate at a constant natural frequency, at a constant frequency, sorry, in a sort of entrainment along the circle. Okay, so just to introduce you into the main results in this model, I need to introduce you some tools. And the most interesting tool here is the order parameter. Is a parameter that we can compute. It gives some light about the how ordered the system is somehow. So the way to construct this is, okay, we consider some distribution of phases around the circle, and we compute the centroid in the complex plane. So this is this sum here. Of course, this is a vector that I'm drawing here. It has some modulus r and some angle phi. You can also see here in the left-hand side. And r is called the order parameter, and phi is the average phase. So phi is a sort of average value of the phases of the oscillators. And r is a very interesting thing, because by definition, r is bounded by 1, and r equals 1 if and only if all the oscillators are concentrated in the same phase value. So this is phase synchronization in this model. So it seems like the order parameter is meaningful, and actually we can restate Kuramoto model in a much simpler way using the order parameter. So by using some algebraic trick due to the algebraic structure of the sine function, we can restate Kuramoto model in this way. It looks like an uncoupled system, but this is not really the case, because the influence of any of the oscillators, any other oscillator, is encoded here in the order parameter r and average phase phi, right? So it's really a nonlinear problem, because r and phi are given by all the population of oscillators. So before entering into more details, I would like to classify which are the equilibria of this system our solution can converge to. So we neglect the time derivative here, and for those equilibria, we obtain this equation. So it looks very similar, very easy to obtain phases from omega by just inverting here the equation. But first, I'd like to draw some conditions, some necessary conditions for the existence of equilibria. If we have an equilibria and we sum here in this equation overall I, then by the antisymmetry of the sine function, we obtain that the average phase has to be 0. It looks something restrictive, but this is not really the case, because you can always make a change of the reference frame and move at the average frequency, so that this condition is always verified. So this is not restrictive, you can always do. But also, since the sine function here is bounded by 1, of course, we get some necessary condition on the natural frequencies. They have to be bounded by k times the asymptotic value of the order parameter. So, okay, as I said before, you can always invert here and phases are given in terms of the natural frequencies. But here we have two different branches. Depending on the branch we take for the inverse, we obtain different value of the phase. So if we take the trivial branch, that is just the arc sign, what we obtain is this expression. So theta is given in terms of omega through this formula, and this can be regarded as just a perturbation of the average phase of the equilibrium. However, we can also use the other branch in the inverse, and what we obtain is a similar formula. We have a perturbation here of the antipode of the average phase. So it looks like all the oscillators are either concentrated around the average phase or the antipode. Okay, but R infinity here cannot be whichever. R infinity is the asymptotic value, the order parameter of the equilibria, and it has to verify this consistency condition. So these three conditions characterize the family of equilibria that takes this form. Here I'm using the set of indices I plus to describe the phases of those oscillators that are perturbation of the average phase, and I minus will be the corresponding oscillators concentrated around the antipode of the average phase. Okay, so before giving some results, I would like to set some notation. I will say that our solution exhibits shows phase synchronization when the difference of phases converges to zero. Of course, in order for this to happen, we require that all the natural frequencies have to be the same, otherwise not possible. However, if the natural frequencies are different, we can always say that our solution converges to a phase log state when the difference of the average phases converges to some asymptotic value. This is what we saw in the video, where all the oscillators rotated around the circle, keeping constant distances between phases, right? And finally, there is a close behavior that is called the frequency synchronization, where the difference of frequencies, time derivative of phases, converges to zero. Of course, any phase log state is a specific case of phase frequency synchronization, but not the other way around. However, if the relaxation of frequencies is strong enough, we can show that this implies the emergence of a phase log state. So we are interested in these dynamics. So we would like to look at some literature first, and here I will talk about this first. I need to make this clear. There are two types of results. One type of result is what I will call for constrained initial data, and by constrained initial data I mean that all the oscillators are concentrated in an arc with length less than pi. Here I'm denoting the diameter of the list of all the initial frequency phases of the oscillators. So all the oscillators are initially confined in a half circle. Under these conditions, in these two papers, they show the following: if the natural frequencies are all the same here, then there is phase synchronization exponentially fast according to this relation here. Otherwise, if the natural frequencies are not the same, we cannot expect, as I said before, phase synchronization, but there is some result. And if the coupling strength is large enough, then there is frequency synchronization exponentially fast. Notice that according to the video I showed before, the large coupling strength is relevant because actually we observe some concentration phenomena and emergence of phase log states numerically in the large coupling strength regime only. This is because there is a phase transition at a critical value of the coupling strength from disorder to phase log states. Okay, this is what we know from literature for constrained initial data, but how about general initial data? So as far as I know, the only two results in the literature are given here. And if we take any initial data that is not too disordered initially, so the order parameter is initially positive, and the coupling strength is large enough, the author could show the emergence of a fixed log state rotating around the circle. So what's the main idea behind all this? So in particular, we can look and the system, the Kuramoto model has a very specific structure. It's a gradient flow. So if we list all the phases into a vector capital theta, it verifies this equation where the energy functional V is given as follows here. So of course it has two components. It has a first component that has to do with the natural frequency itself, and the second part is the term corresponding to interactions between different oscillators. As you can see, this is not convex because cosine function here is not convex. And this is the main problem behind the confinement assumption of the initial data. Many people assume this in order to have some convexity here. However, if initial data is general and spread out all around the circle, there is some very interesting results by Logacievi. And since the Kuramoto model is a gradient flow given by an analytic potential V, V is analytic in this case, then the potential verifies the Logacievi gradient inequality. And in particular, it can be used, and these authors use that, in order to show that if you have a trajectory of the system that is bounded, then it has to converge to an equilibrium, right? So the main idea behind this result is that for large enough coupling strength, you can show that the diameter keeps bounded and your solution will converge consequently by Logaciev inequality towards a global equilibrium. The main problem here is that, of course, you don't know how much time it takes for your solution to enter into the basing of attraction. It means to a neighborhood where the Logaciev gradient inequality is verified. So this result is not in particular quantitative, and we are interested in quantitative results. Okay, so I now move to the macroscopic Kuramoto-Sakaguchi equation. So this equation describes the evolution of a large population of oscillators, and instead of a system of ODEs, I have a partial differential equation that has this form. This is a Vlasov equation for the distribution function f of finding oscillators at time t with phase theta and the frequency, natural frequency equals omega. This is a continuity equation where the velocity field is nonlinear, self-generated itself by the solution. So here this rho is just the integral with respect to omega, so it's the macroscopic density of the population. And also you can integrate with respect to theta. What you get is another distribution of probability. This is the distribution of natural frequencies. Of course, it does not depend on time because in the equation, as you can see, there is no derivative with respect to natural frequencies. This means, in particular, that there is no mixing between different values of omega. So since I look at theta as a periodic variable, my phase space will be a cylinder. And we have theta as a periodic variable and omega. This will be my variables. And for this system, the well-postness was first proved by Lancelot in 2005. So in particular, you have measured value solutions, L1 solutions, and many others. Because mainly here, the kernel is a sine, and sine function is very smooth. But the most interesting thing is that this system approximates the microscopic dynamics. So when there are many, many oscillators, you expect that this system approximates what you saw at the microscopic level. And in order to do so, we have to do the mean field limit. This is a very old technique that is due to Dobrushan and Neunzer in particular. And it goes as follows. So first you compute a solution to the microscopic equation, so Kuramoto model, and you compute this atomic measure. It's a measure that is concentrated over the microscopic trajectories. This is called the empirical measure, and it's very easy to show that it's a solution to the Kuramoto-Sakaguchi equation, right? And there is a stability estimate so that you can compute how far your solution to the Kuramoto-Sakaguchi equation gets from the empirical measure. And in particular, if your initial data is approximated by a sequence of empirical measures, you can do so by a law of large numbers. If mu 0 n converges to f0, this keeps going on for all times. And this is what's called the mean field limit. No? So the empirical measures approximate as the amount of particles tend to infinity the macroscopic Kuramoto-Sakaguchi equation. Okay, so again, I will pass through this very fast because I'm trying to identify what's the order parameter and the family of equilibria, but it's essentially the same. We have now not a discrete configuration, but a continuous configuration of oscillators, and we compute the centroid. So we have a vector with a modulus R that is the order parameter. I use capital R for continuous variables, and phi is the average phase. So again, some trick, algebraic trick with the sign function shows that the equation can be written in this equivalent way. And if we look for equilibria, we can neglect the time derivative, and we obtain this equation. Again, we can try to invert this equation and find what's the equilibria like. And so the first thing, we can see some necessary conditions. The first one is the distribution of natural frequency has to be centered at the origin. It means the average phase is, the average of natural frequencies is 0. And also the support of the distribution of natural frequencies has to lie in this interval depending on k are the asymptotic value of the order parameter. These are the analog conditions to those I saw in the Kuramoto model at the discrete level. So again, it's very easy to invert here, and given any theta and omega in the support of the equilibria, you can find theta in terms of omega by inverting here in this equation, and we have, again, two possible branches. Either you have a perturbation of the average phase, or you have a perturbation of the antipode, okay? So what we have is that our equilibria look like this. We have that for every omega, the distribution with respect to theta is a Dirac mass that is concentrated either around theta plus or concentrated around theta minus, okay? Again, we have some consistency condition here. And in particular, I'd like to emphasize here, in order to ensure the existence of some R infinity verifying this equation, a sufficient condition is that K is large enough. So the large coupling strength guarantees the existence of equilibria, and all the equilibria looks like this, like in this square. Okay, but very interesting thing is, like we see in the simulation, there is no, it seems all the particles concentrate around the order parameter. It means that the G minus plus should disappear somehow, and we will show this in the sequel. So now I'd like to show the main results. That has to do with the mass concentration phenomena, and how I finally use this to show the convergence towards an equilibrium. Okay, so first of all, I would like to use some notation all around these parts. So if we look, we have the circle here, and we have the average phase and the antipode. I will construct two intervals. The first interval, L plus alpha and L minus alpha here, are just some metric neighborhood of the order parameter, the average phase and the antipode, where the angle is given by alpha, and the angle actually is pi over 2 minus alpha for technical reasons, but it's described in terms of alpha. So what we see in the simulation is that it seems when the coupling strength is large enough, all mass enters into the blue part, so the L plus interval. So our result looks like this. If we take any C1 solution to the Kuramoto-Sakaguchi equation, so that the distribution of natural frequencies is compactly supported in this interval, then for large enough coupling strength, and we can quantify how large it has to be, we quantify this in terms of the support of the natural frequencies and the initial value of the order parameter, then the mass concentrates exponentially fast in the L plus interval, so around the order parameter, after some time t0 here that we can quantify. So there is the emergence of mass concentration. And what I finally would like to show is that under the same condition, not only concentration phenomena takes place, but also we can show that our solution converges towards the unique stable equilibria, so the one without the theta minus parts, so the one concentrated around the order parameter, and the convergence is exponentially fast. Here, I will use some transportation distance in order to Wasserstein type distance in order to quantify the convergence to equilibrium. Later, I will show which is this transportation distance. But before showing the result, I would like to draw some small relation between the Kuramoto model at both levels, discrete and continuous. So this is the energy functional for the Kuramoto model. There is a gradient flow. And if you differentiate the energy functional, it's negative and it's given by minus the dissipation functional, written like this. So we expect that at the macroscopic level, we get something similar. So why not we define the candidates to energy and dissipation in the following way, just substitute sums by integrals here. So if we do so, we obtain this energy functional V and this dissipation functional D. This red part is just because for technical reasons, this does not make sense for thetas in the unit torus, but you can always lift and look at theta in the real line and this makes sense. Okay, so if we try to compute some gradient flow, and the classical ways to compute gradient flows with respect to the Wasserstein distance, we obtain this continuity equation where here we have the first variation of the energy functional. Explicitly, you can compute and you get the Kuramoto-Sakaguchi equation, except for a term that involves a derivative with respect to omega. So the Kuramoto-Sakaguchi equation is not really a gradient flow for the Wasserstein distance associated to this energy functional. But still, it's very interesting to see that the entropy dissipation relation is verified. So in the last few slides, I would like to show how we can use this entropy dissipation relation in order to implement some entropy method and show the concentration phenomena and convergence towards the equilibrium. So all around this part, I will assume some large coupling strength regime. Here, lambda will be a parameter between 0 and 1, but at the very end, lambda will be related with the initial value of the order parameter. So at the end, we will have the hypothesis I showed before in the lemma. Okay, and a very interesting thing is that the dissipation is related to the slope of the order parameter through these relations. So modulo a lower order term, because we have large coupling strength, dissipation and order parameter, slope of order parameter are barely the same thing. So I will say dissipation, large or small dissipation, but actually I will work with large or small slope of the order parameter because the order parameter is a more classical thing. No? It has been used for a while. So the main trick is, okay, let's look first to an integral with large dissipation, so large slope. If at some time the slope is large, we expect that the order parameter keeps increasing. And actually we should be able to quantify the growth. And this is what I'm claiming here for large coupling, large slope of the order parameter, large dissipation. You have some control on the growth of R. But unfortunately, we cannot ensure that our solution will have large slope of the order parameter for all times, because the order parameter has to be bounded by 1, and this condition, if it happens for all times, gives a contradiction, right? But what happens if the slope of the order parameter is small? It might decrease, R might decrease, but it cannot decrease more than lambda R naught. So we have a lower uniform bound of the order parameter, and this guarantees that the solution is not behaving in a bad way, in the sense that it gives a regime with very disorganized information, so R very close to 0. However, what happens really if the slope of the order parameter is small? So if the slope of the order parameter is small, actually something good happens, and the good thing is that the L2 norm of the solution along the L- intervals, so intervals around the opposite of the order parameter of the average phase decrease exponentially fast. So in particular, mass in the antipode will decrease exponentially fast. Unfortunately, we cannot stay also here for all times. We may switch from large dissipation to small dissipation. And this is the main problem here. And also another problem is what happens when mass escapes from the antipode of the order parameter. Will it enter into the L plus interval, or will it stay in the interface? So between the L plus and the L minus interval. So in the last result that actually I'm not going to discuss about because I don't have enough time. What we show is that this mass actually enters into the L plus interval. So after it escapes from the L minus interval, it enters into the L plus interval. And the main idea is that we can construct some sets we'll call attractor sets that are neighborhood of the order parameter that that gets all the mass in the regime of small dissipation. So at the end, we have more or less a clear picture of what happens if the dissipation is large or small, and using a green procedure like in many other entropy methods. In particular, here I mentioned the work by De Villet and Villani for Boltzmann equation. You can get some final quantitative estimate of concentration, and we obtained the thesis of the lemma I showed before. So there is emergence of concentration around the order parameter exponentially fast if the coupling strength is large enough. So finally, how can we use this in order to show the convergence towards the unique stable equilibria without the theta minus part? So the main idea is, okay, let's first look at what is this appropriate transportation distance. Of course, this is not the classical Wasserstein distance, but it's some version that I will introduce right now. Because as I said before, the classical Wasserstein distance is not very well behaved with this equation. So in order to introduce this distance, this is called the Fiber-wise Wasserstein distance. It was introduced by myself in a former work, and also by my collaborator that I didn't mention before, by J.Morales from the University of Maryland. This distance looks as follows. So let's take first a couple of measures, probability measures on the cylinder. These are our phase space, theta for, the torus for theta, and omega is moving in R in the real line. So if those measure verifies this constraint, and this means that both have to enjoy the same marginal with respect to omega, this means they have to enjoy the same distribution of natural frequencies, then we can do the following thing. We can compute the family of conditional probabilities with respect to each value of omega, and this provides a family of probability measures on the torus, so just measures with respect to the variable theta. And then we can compute the quadratic Wasserstein distance in the torus between any member of this family. This is what I'm reading here. And at the end, we glue all the information together by taking a weighted L2 norm with respect to the distribution G of natural frequencies. And I claim that this is a metric in this set, in this space. So this becomes a metric space. And the interesting thing is that the following takes place. So we can find some transportation dissipation inequality. And specifically what we have is that the transportation between the transport distance here that I just defined, the Fiber-wise Wasserstein distance, can be controlled by the square root of the dissipation functional. And this is reminiscent of the Talagrand log Sobolev inequalities that in particular you can find in this work by Otto and Villani in 2000 for other systems. Okay, so as long as we have some control on the dissipation, we will have also some control on the transportation distance.
Sorry, David, I need you to wrap it up if you can. Thank you.
Thank you. So just one slide, thanks. So finally, we have some some relation between the transportation distance and the dissipation functional. And what I claim is the preceding concentration phenomena guarantees a well-behaved dissipation functional. And what we have is this negative ground-wall inequality. I say negative because here we have a negative term, except for a remainder, but very likely the remainder depends on the mass outside the L plus interval that, due to the lemma, concentration lemma, converges to zero, decrease to zero exponentially fast. So this goes to zero exponentially fast. The dissipation functional consequently goes to zero exponentially fast. And this means that the transportation distance goes to zero exponentially fast. So at the end, we recover the convergence, exponential convergence towards the equilibria after the time t naught, quantified by the concentration result. So at the end, our result claims the following. So for genetic initial data, we only have to assume the FEC1 in the large coupling strength regime, and this is a strong restriction, but also is something we expected because as we see in the simulations, only for large coupling strength regime, we can see some aggregation phenomena and some convergence. We can quantify the convergence towards the equilibria after some quantified time t naught. That is precisely the time that takes for your solution to enter into the center of the basing of attraction, so the convex part of the energy function. So this is everything I wanted to talk about. Just to conclude, I'd like to draw some relation with the gradient flow structure that was not verified by the Kuramoto-Sakaguchi equation. As I said before, Kuramoto-Sakaguchi equation is not really a gradient flow for the Wasserstein distance, but actually, if we use the fever-wise distance, we are working here with J.Morales and some other collaborator of mine, Jan Petschek, and we are exploiting this distance to show that this problem and also many others can be regarded as gradient flows with respect to the fever-wise distance, and we can use classical methods to derive the convergence towards the equilibria. So thank you so much for your attention.